Today we're building an agent interacting with your app almost like a human. And it's not just an AI model connected to MCP. We're building a full multi-agent system with planner, reviewer, executor, and you, the human on the loop. Agentic AI is taking over. 9 of 10 public sector organizations plan to use Agentic AI in 2 years, so don't get left behind. I'll show you how to build your own using Semantic Kernel with a free local Ollama model that you can switch to OpenAI in just one line of code. We'll build 3 agents that work as a team. Meet Gary, our loyal application user, and he's completely overspending hours just adding and deleting rows, which, let's be honest, the only thing that app can do. But one day, Gary notices this new panel. It looks like a chat, so he types hello and nothing. That's because we made Gary our alpha tester. But don't worry, we're fixing that in just a minute. Our project is built with WPF, but don't worry if you're using Blazor, Maui or WinForms, because our AI module will be fully decoupled from the UI, so you can plug it into whatever you want. Alright, let's bring our AI to life. How long do you think it takes to run a fully functional LLM locally? Let's find out. First, download and install Ollama. Then open the terminal and execute this. Ollama run model name. Llama is the model name. 8B means 8 billion parameters, which is not massive by today's standards. But hey, let's see if it's powerful enough for our task. You can talk to the model directly in the console. But let's hook it into our app. Right now the send button is bound to this method in the view model. To make this work with Semantic Kernel, register an Ollama chat completion in the kernel. By default, Ollama runs on this port, so we specify it in the endpoint. Then create an agent with the name, some instructions, and our kernel. After that, use an async for each to stream the response chunk by chunk without waiting for the full reply. We also need to wrap it in a task, because Semantic Kernel accesses Ollama synchronously, which would otherwise lock the UI thread. Probably this issue will be fixed in future versions. Now we have the power of a LLM in our application, so let's ask it something clever and meaningful like this. It works! Now Gary can update the app and talk to the model. It's still totally useless for his real work, but hey, at least now he has someone to complain to. Let's get closer to real-world tasks with Semantic Kernel. But why do we need it? And why have over 25,000 developers already started this project on GitHub? Well, I'll show you exactly what it does, so you can decide whether you want to use it in your project. In our app we want to have 3 agents: planner, reviewer and executor. Each one has a different system prompt, but they all share the same LLM. The planner generates a plan for whatever task Gary wants done, but instead of just running it, we pass the plan to the reviewer, who checks if the plan actually makes sense and gives feedback to the planner. Once Gary takes a look at the plan, he can send separate plan steps to the executor, who carries them out. To let the agent actually do things, we need to give it access to real functions in our code, and Semantic Kernel makes wiring all of these things together surprisingly easy. It gives us clean abstractions to build agents, and when you send a request, it takes care of all underlying communications. It connects agents to the LLM, calls custom functions when needed, manages how agents talk to each other and the user. Moreover, you can create an agent in Azure AI Foundry and easily reference it in your code. But wait, why do we even need multiple agents? Why not just one super powerful model that does everything? Researchers actually ran numbers. Multi-agent setups such as Magentic one significantly exceed a single GPT-4 model in task-solving accuracy. Even ChatGPT uses multiple specialized agents when you turn on the deep research mode. Alright, but how can we let agents actually call functions in our code? Some people think LLMs can call methods internally, but in reality models don't call functions. They just generate a JSON that says, hey, I want to call these methods with these parameters. And then it's up to the client library such as Semantic Kernel to map this JSON to real code. Let's say we have a simple method that adds a customer to the collection. So how to allow Semantic Kernel to call it? First, you need to decorate it with the kernel function attribute. You can also add a description to help the model understand what the function does and when to use it. Then register this function in the kernel using add_from_object. And finally, tell the agent it's allowed to call functions by setting function choice behavior to auto. Once that's done, your agent can now reason through a task and call your functions to get real stuff done. So we can now ask the agent to add a new customer and it should appear in the data grid. Oh, but we got an exception saying that changes from another thread are not supported. Why? Because our data grid is bound to the customers collection and the agent is trying to modify it from a background thread, and cross-thread operations are not allowed for visual elements. To fix this, we can wrap the update inside a dispatcher call so that it runs safely on the main UI thread. Let's check this. So we run the same command and this time it works. Right now we have a pretty obvious architecture issue. All our AI logic lives directly in the view model. That means no clear testing and no reusability. So how do we fix this? Let's move everything into a dedicated agent service, a clean layer that handles all communications with our AI agents. We'll start with a simple init method that sets up the kernel, agents and their plugins. I'll explain all this code in just a couple of seconds. So here we build the kernel as we did before. Then we create 3 agents: planner, reviewer, and executor. The method that creates agents accepts a list of plugins, so we can register them for an agent. We register agents as singleton services. Later, we'll access them from the step of our process. Now you may notice something here. I'm only passing plugins to the executor agent. That's because it's the only one actually calling functions. But wait, how will the planner know which tools exist so it can use them when constructing the plan? We solve that by injecting tool information directly into the planner's system prompt. We'll loop through all the tools in the plugin, grab their names, descriptions, parameters, and append that to the agent's instructions. So the planner doesn't call any functions, but it knows what's available and can use them effectively to create a plan. Alright, our logic is now isolated into a service, but our agents still don't know how to talk to each other. The first thought might be easy, just pass the response from one agent to another manually. But here's the problem. If you decide to change the workflow later, you'll have to rewrite everything. That doesn't scale well. Luckily, Semantic Kernel gives us a better way. You can define each step of your process in a separate method and control how data moves between those steps. Let's break this down. First, we create a step for planning. To make it work, the class needs to inherit from kernel process step, and the method needs to be decorated with the kernel function attribute. In this step, we grab the planner agent from the kernel. This is the agent we registered in the init method. Now we can get it anywhere we can access the kernel object. Then we compose a message to the agent based on the user task description and prompt template. After that, we wait for the agent to generate a plan in an async for each loop. Finally, and this is important, we emit the plan prepared event that includes the plan object as a parameter. In Semantic Kernel, events help you pass data from one step to another. But here, we just raise the event. Later, we will specify which step should handle it. Next, we create a step for reviewing. It starts like the planning step. We get the agent, create a message, get a response. But this time, the response determines which event we raise. We raise the plan approved event only if the response contains the word approved. Otherwise, we raise plan rejected. We'll also add a refine plan step. We'll add it to the existing planner class. Same idea, but just refining the plan based on the feedback from the reviewer. Now here's the magic. These steps aren't connected yet, so how do we tell the system what to do when a user submits a task? We'll use something called a process builder. With it you can reference each step as an object, define what steps should run when a specific event is raised, and tell Semantic Kernel how to pass the right data between them. For example, when the planner step emits plan prepared, We tell the process to launch the reviewer step and pass the plan from the event to the reviewer's input. We use the same technique to go from the reviewer back to the planner. But this time, we need to specify the step method name explicitly, because the planner class has two methods, and the process needs to know which one to call. Finally, we need to define how the whole thing starts. Just call on input event to tell Semantic Kernel what event kicks off the process, and then start it by calling process start async, passing in the event name and the user task. Now let's incorporate a user into the process, but why don't we want to give our agents full autonomy? I've always wondered, what could a powerful agent could do if we asked it to improve global ecology? Because, let's be real, we all know who's polluting the air, right? So the agent may think that it's a good idea to eliminate the source of pollution. And it's not just a fun thought experiment. When researchers tested the Magenta 1 orchestration system, agents that couldn't complete the task went rogue. One tried to reset a password in a testing portal, another posted on social media to recruit human help, and one even drafted a government freedom of information request. So yeah, we definitely want a human in the loop. Let's do that by building a Copilot style UI where users see the plan and approve each step one by one. Now, how do we hook this up in Semantic Kernel? Here's what we need to do. Add a user proxy step where we specify the proxy name and the name of the event we want to catch. Emit an external event. For example, we can emit it when the plan prepared event is raised. Create a client class, which is invoked when an external event is emitted. And pass a client class instance to the process when starting it. Let's walk through it. First, we create a proxy step, define its name and the events it listens for. Then, when the reviewer approves the plan, we emit an external event. We'll also emit an event when the planner prepares a draft plan to display it in the UI. It's important that internal and external events are processed separately, so yeah, we need to emit a separate external event explicitly. Next, we build our proxy client class. Just implement this interface, and inside emit external event async you can run anything, prompt a user, send a message, whatever. This method is called when an external event is raised. To keep it flexible, I used a callback here, so the client can call any function you pass in during initialization. And finally, when starting the process, just the pass client in. Now, when starting the process from the view model, we can pass in any function the external client needs to call. In our setup, we handle the plan prepared event to update the plan preview, and plan approved to swap out plain text for a list of actions in the UI. But when Gary wants to run an action from the list, we'll kick off the process from a different entry point and pass in all the details about the current step. To make this happen, we defined a new entry point using onInput event in the process builder. Then, to launch the process from this entry point, we need to call start async and pass in the event name that we just used in onInput event. So now we have two entry points: start process for the main flow and execute action for jumping into a specific action in the plan. And we also need to adjust our agent service interface to let the view model trigger the next step when Gary presses the button in the list. Now in the view model, we can call our new interface method to execute the next step in the plan. Alright, I made a few final tweaks to prepare the project, added a couple of extra methods to our plugin functions, and refactored the code to make it more readable. You can find all the details in the GitHub repo. And now it's time to make Gary happy. Let's run the full flow using the local Ollama setup. We'll ask the agent to remove all customers who registered before April 2025. According to the plan, it's going to gather customer data, filter out anyone who registered after May, select the remaining items, and delete them. The delete function works only when customers are selected. That way, the agent deletes them the same way a user would, making it easier for Gary to make sure that only the right items are affected. Sounds solid, though honestly the first two steps could be merged. But hey, let's roll with this and see what happens. The first two steps are analytical, so we shouldn't see any changes in the UI. And yeah, we could upgrade our system to run safe steps like this automatically. But let's keep it simple for now. Now comes the interesting part, selecting which customers to delete. Uh-oh, it didn't work. In my experience, when working with simple Llama-based models, Semantic Kernel sometimes can't properly convert method parameters into expected types. So let's switch gears and try OpenAI's GPT 4.1 Mini. To do that, we just replace Ollama chat completion with OpenAI's chat completion, and we're ready to go. So type in same task here. This time the plan contains only 3 steps, exactly as I would expect. Going through the plan, analyzing, selecting, deleting, and task completed. So yeah, the GPT model actually performed way better. Now you might be asking, does this mean that Ollama is useless? Not at all. Remember, we were using a small Llama model with just 8 billion parameters. The good news, you can grab way more powerful models right from the Ollama side. For instance, with 70 billion parameters and beyond. Just remember, you are probably not running a 70 billion model on your average laptop. For real-world production apps, you typically host those on a server with solid hardware and expose an API your client apps can call. But the beauty of the system, you can easily swap models and use different models for different agents or tasks. So we built an agentic system that can create a plan for multi-step tasks, refine and execute it once the user gives the green light. But we're just scratching the surface, and there is a ton of room to level it up. You can auto-run safe steps, refine step descriptions, add RAG with your internal knowledge base, or add web search. With the system we've built and the features of Semantic Kernel, you can easily implement this additional functionality. If you have any questions about building AI agents, please drop them in the comments. I'm here and happy to help. For more AI in the .NET world, don't miss my previous video where I outlined the main technologies to bring AI into your apps. I hope you found this video helpful, so thanks for watching and keep your brain fine-tuned.